Dear student, in this video, we will understand few basic concepts before start designing of FIR filter. Whenever you want to design a filter, you have to know the specification of the filter. Suppose if you want to design an ideal low pass filter, in this case the specification is omega c, which is a cutoff frequency, and in the case of ideal response, pass band amplitude is always 1 and stop band amplitude is always 0, and there is a clear demarcation or sharp transition from pass band to stop band. So when you include the negative frequency also, so in this case the ideal low pass response is of rectangular shape. Also, in the case of FIR filter, you know that for designing a exact linear phase FIR filter, the impulse response should have equal amplitude at opposite end. So if you choose the center of symmetry here, so the amplitudes are equal on both the sides. So center of symmetry matters in the case of exact linear phase. And this particular response, frequency response, is termed as the desired frequency response because it is in actual desire whenever you go for the designing of a filter. If you want to design a low pass filter, you want the clear demarcation between the pass band and stop band. Means if you want to the pass a frequency, it should be pass fully, and if you want to stop the frequency, all the components of that lie in the stop band should be completely rejected at the output. So that's why D is written here, that represent the ideal, or D represent the desired, and this is the desired frequency response. So the mathematical expression of the desired frequency response is expressed in its Fourier transform formula, where n goes from minus infinity to infinity as SDN. SDN is a desired impulse response corresponding to this desired frequency response. Okay, so when you want to find out HDN, what should be the desired impulse response corresponding to this desired frequency response, you have to take the inverse Fourier transform. So as per the inverse Fourier transform, you have a formula as 1 upon 2 pi minus pi to pi HD e raised to power j omega, e raised to power j omega and j omega. This is because the Fourier transform is a periodic signal with the period of 2 pi. Okay, so the interval during calculation of the impulse response, we get minus pi to pi range in the formulation of the inverse Fourier transform. Now, as this can be seen in this formula, this is a formula for the inverse Fourier transform. Now, when you put the value of HD omega, which is 1 in the pass band and 0 in the stop band, after putting this value, you will put the value of omega as a limit minus omega c into omega c. The value is 1, otherwise it is 0. So this integration will be calculated within this range, and after integrating this thing, you will find out this type of form, which is basically a sinc function, and this sinc function will look like this. Meaning is that in this case, this is the desired response. This desired response have repetition because it is a periodic signal. It varies from pi to, so one period is in this region, and after this it will start repeating itself. So when you see the inverse Fourier transform of this rectangular function, it will look like this. It is a sinc function. Sinc function means the amplitude will decay sinusoidally and gradually. on both the side. Now what you are seeing here? You are seeing here they are the infinite number of coefficients. In the case of FIR filter, FIR filter means finite number of coefficient in its impulse response, means 1 1 1. This is a finite length, so it will be expressed as 1 plus z inverse plus z minus 2, means a polynomial hz is of, it should have finite number of terms. So these polynomials coefficient is represented here. The meaning is that in case of ideal frequency response, whenever you find out its corresponding time domain counterpart, you find that there is an infinite sequence of the coefficient, and so the filter is not the FIR filter. In the case of FIR filter, you must have some finite number of coefficient. So how you can find out the finite number of coefficient? You will pass this particular signal through a window, and the magnitude of this window is 1, and after that the magnitude is 0. So when you pass this particular signal to a window to make it finite, make the impulse response of finite length, the rest values, because they are being multiplied to 0, become 0. So the response will be of this particular shape. Because of this abrupt truncation of sinc function, the shape of the desired response will not remain the same, because the desired shape have this particular response. Now you are reducing the impulse response length to make it finite. So this particular, when you take the Fourier transform of this signal, it will result into the different shape than the ideal one. So now it can be better illustrated here. Now in this case, when you truncate, there will be the response, means you will see there are the ripples in pass band and stop band because of abrupt truncation. If you truncate, or if you increase this window length, means more number of coefficient you are involving. So in this case, these ripples, the amplitude of these ripples decreases in both pass band and stop band. And when you include all the impulse, means when you take the window of infinite duration, so in that case you will get the ideal response. So means if you are omitting the coefficient, you are visualizing the ripples in both pass band and stop band. So this is a deviation from the ideal response, but we have to make a compromise because we are going to design a finite impulse response system, and that's why we are seeing the ripples in pass band as well as in stop band, and this phenomena is known as Gibbs phenomena. So thank you.